So I'm going to talk about this, what we call hyperscale NAS, and solving data aggregation problems, and the S3 service that I recently developed for the product. So this is very similar to stuff you've heard over the last couple of days, where we view this very much as a data aggregation problem. How do you get to data silos? How do you solve the silo problem? How do you bridge to cloud? How do you aggregate data that's spread at different locations? And I'll spend a little bit of time talking about the S3 service. I have no intention of making this an S3 tutorial. So if you have questions about S3, that's fine, but I'm just going to talk about more about the architecture of the service, not so much about the details of the implementation. So the fundamental problem when you're building large language models and AI is you've got decentralized sites. It's very different from the traditional HPC market, where you tend to have a single location where you have thousands of servers interrogating perhaps a single file, probably not that many users. It's trying to filter through the data, maybe trying to pull data from multiple sites or aggregate multiple sites. The typical HPC problem or genomics problem or post-production in media and entertainment is you're taking maybe a single file, you're chopping it up into thousands of small files, you're performing transformations. Then you may or may not discard the data. You may have to recompile the data into another data set. So this is the typical, I think is a typical AI pipeline. I'm not an AI expert, but you're trying to aggregate data from various places, various silos. You're trying to clean the data, either filter out outliers to stop model skew, or you're trying to fill in gaps in your data model. You need to do classification or regression. I didn't really want this to turn into an AI tutorial, but my understanding is regression is mostly about prediction, and classification is more about pattern recognition. You're going to take the existing data, you're going to try to train your model, import the data into your model, and then you do inference, which is basically taking your model and trying to apply it to new data. But the fundamental problem we're trying to solve at Hammerspace is how you take all this data that's in different locations, maybe in clouds, and you try to pump it into the system with high performance and try to remove the separation of all the different namespaces. So again, you have in your typical enterprise infrastructure, you tend to dedicate storage to applications. Maybe you have SQL servers, maybe you have NoSQL, maybe you have home directories. You tend to locate the data on different NAS boxes because you want the NAS box to perform a single function. You don't want the CPUs split between different workloads. And in its typical NAS product, you're dealing with both data and metadata coming from the same storage box or storage cluster. So you're working the box pretty hard if you want to drive the data out. And of course, you don't have the single namespace, or you may be aggregating data from cloud or to cloud. And you need something that's going to solve those problems and bridge those problems. So we've heard a lot of talk. Tron gave a talk yesterday on pNFS. I don't know why people always talk about pNFS and 4.2 in the same, it's like one thing. It's actually two different things, at least in my mind. So what pNFS does is separates the data path from the content from your metadata. And by metadata, we mean the attributes of the file, the timestamps, the size, the access control, the directory structure. So in a typical file system, you're mixing the metadata and the directory structure with the content. And you have to go through all of those things on the same box, through the same CPU, through the same memory. And it limits your performance when you're trying to push that data onto the network. With pNFS, you separate the metadata from the data, from the content. So all of your attribute requests, whenever you ask for timestamps, you want to interrogate a directory, a list of directory, it goes to a separate system, the metadata server. You get back a handle, and then that handle is given in what they call a layout in pNFS, and it allows the client to attach directly to whichever piece of storage happens to have that content. And in the Hammerspace system, we have a process called assimilation that allows us to take the metadata from any NFS v3 or SMB server and import it into our file system. So our file system, our metadata server, is essentially a key value store that only has metadata, has no content whatsoever. So while you're doing metadata operations, you're talking to our metadata server. When you're actually reading and writing content, you're talking to the original storage that had that content. We don't move any of the data. All the data remains where it was in the original storage. And the idea is that you can scale out the I/O path as much as you want because it's the client that goes direct to the content. We are not involved in going to the content. Any questions on pNFS? Because that's a key aspect here. Is I'm going to talk about how well this scales out, and it's really important to understand you can keep adding storage nodes, and we are not in the data path. So when we talk about linear scalability through our system, it's because we're just not involved in I/O.
You generally have this, there's going to be some activity on demand side and output.
And you saw this slide if you were at David Flynn's talk. This is Meta for their Llama AI system. People often talk about how well the system scales out in the number of nodes, 10 nodes, 15 nodes, 20 nodes. Currently, Meta is using a 1,000-node cluster with, I think it's around 35,000 GPUs, or is it 24,000 here? I think their plan is to go to 1 million GPUs. We're seeing linear scaling, again, because we're just not involved. It's just a client talking to whichever server. I think they're using Penguin Computing OCP servers, Open Computing rack mount servers. But this is basically our proof of concept that you can get massive, massive throughput using our scale-out system. Any questions on this?
In contrast, the drive has to make a decision and reaction.
And this is kind of the bridge to the S3 part. So with Meta, it's mainly an NFS workload. With some of our other customers, they are using Hadoop, HDFS, and they want to consume data using S3, using distcp. They may want to aggregate data from or to clouds, which we also use S3. Within the product, we use S3 for the global namespace to, if you have different sites, we use S3 as the replication engine. It works pretty well because you've got your HTTPS, you've got your encryption over the wire. It's very high speed at moving data, so it works really well for moving data from different sites into, so our namespace, it doesn't matter what site you look at, you see the same global namespace. It aggregates everything across all sites. So there's multiple uses of S3 to push and pull from the cloud, to do replication between sites, and also to pump data into the AI training system.
Even as you get to live for one particular vendor, there is some variation of when operations actually complete. So you end up having to put around some pretty big clusters.
And I'll talk a little bit about the choices we made for S3. I spent some time looking at HTTP servers. So essentially S3 is a protocol that goes over HTTP. So at the front end of all S3 servers, you basically have an HTTP server. I looked at various implementations in Go and Java, different languages. It works out well for us to choose Nginx because it's written in C, and a lot of our code is written in C. Nginx is an extremely scalable performance server. The guys at Nginx or F5 claim it's the most deployed HTTP server in the world. It supports multi-tenancy, so you can set up multiple containers within Nginx just through the configuration file. As an implementation, It uses epoll and k-event and asynchronous events to get concurrency. It actually has some multi-threading now. I put up it's single-threaded. The core of Nginx is single-threaded, but just like Samba, it uses threads for AIO. It has thread pools at the back end to do AIO. In terms of the S3 service, we support all the things you might expect, buckets, objects, versioning. I've spent a lot of time, for those that know me, on access control and identity management. I worked on ZFS and Solaris, done various projects where I have to implement ACLs. So one of the things I did here at Hammerspace was to integrate the ACL management. People talk just if you were in the BOF. People were very concerned about how you integrate identity management and ACLs between S3 and NFS and SMB. There are some issues in terms of, S3 doesn't really support groups per se, and they have role-based administration, so there may be some things that I need to fix up. But the basic ACLs for the canned ACLs and the predefined ACLs, or they can send you an XML file with an ACL, all of that stuff is integrated in the service. The back end is purely, the file system, pNFS, is purely ACL-based. You'll remember this from Infinite Volume when I tried to push unified ACLs into NetApp and get rid of security styles. This is the same idea. So the file system, so the namespace is a single namespace now. We used to have a separate S3 backend, so you couldn't see the SMB and NFS data if you're looking at S3 data. Now it's all just one big namespace. All three protocols, NFS, SMB, S3, are looking at the same file system hierarchy. It's just been treated according to the protocol requirements. So directories are prefixes. It has snapshots, it has versioning. The file system supports individual file versions. And it will use that technology if you are multi-site and it's presenting a global namespace. If you modify the same file at different sites, it will create a conflict file. One of them will become the current version, one of them will become the previous version. So you don't need to worry about losing stuff because two people committed changes to the same file at the same time. The file system also supports tags. So the S3 tagging system is fully supported, whether that's user-defined metadata tags or custom tags. We have a system that we call objectives. It's basically policy management, so all the lifecycle policy stuff about tiering and moving data and relocating data and requiring data to exist on certain sites is all done through a scripting language called HammerScript. And underpinning that is a system of objectives. So I've integrated the S3 service with that, so you can do lifecycle management through S3. And I've also integrated it with Active Directory. I used the Winbind service from Samba because we use that for our SMB service. And it's using the same model to create an equivalence between S3 UUIDs and SIDs and local IDs, GIDs and UIDs. So it doesn't really matter which protocol you come in over, your identity within our system is the same. We create an equivalence within the file system. I did this work also in ZFS. I don't know if the ZFS port to Linux did this, but in Solaris, we called them ephemeral IDs. There's a 64-bit ID, and you just create an equivalence between any kind of identity, whether it's a UUID, a SID, or a local POSIX ID. Any questions on any of that?
How do you implement backup policies?
They're stored as, how do I implement bucket policies? So the bucket policies are stored on the file system as an objective. So if you have a life cycle associated with a bucket, if you want data to be deleted automatically, or you want it moved to different tier, I receive an XML definition of what the policy is. I then execute HammerScript, and that sets an objective within the file system, and the file system has an implementation we call alignment, and it tries to align the data with the policy. So if the data is not supposed to be there, it will be deleted. If it's supposed to move to another tier, it will move. The file system is the engine taking care of all of that. That's one of the differences with our product and other products is normally you have your lifecycle management as a layer that sits on top of your file system. In our case, the objectives and the alignment and the policy management is actually implemented inside the file system. So you just tell the file system what you want the objective to be, whether it's resilience, whether it's tiering, and it will try to make, we have an engine called the data mover that tries to make that policy correct.
So my question was more on the access restrictions in bucket policies, where you can say that user has access to that prefix and so on, and how that maps to
So, the question is, if you're using like a role-based restriction or you're using a prefix-based restriction, how do I enforce that on the bucket? I need to figure that out. That's actually not implemented yet, but it is on the roadmap to do that. Right now, it's just purely access control. So you can set ACLs on things, or you can deny access to a bucket through the ACL, but like you can through the share ACL. The role-based management, I haven't done anything with yet. Here's another question.
I think you mentioned how different users between NFS and SMB and S3, that they had different identifiers that they call them equivalences.
Yeah, so I create an equivalence.
So is that mapping, is that something that the administrator has to set up?
No, it's done in the file system.
No, in the file system.
You don't have to, there's no configuration. So over S3, you typically come in with an access key, and you have pre-configured the system with the secret key. So the client knows the secret key, and the server knows the secret key. As you connect, you give me the access key and a header that's encrypted using your secret key. I decrypt the header, and you become authenticated. And there is a configuration file where that access key is mapped to an identity. And that identity is maybe a SID or a Windows name or a Unix name or a Unix ID. I can then look that up in Winbind, which is our basically back-end naming service. If it's an Active Directory, I get back a thing called an auto-RID. In Solaris, we call them ephemeral IDs. That gets stored in the file system. Whenever the file system is accessed using, say, another Windows identity, it has an identity structure that has the same mapping. It maintains the mapping. It actually, the UID is actually slightly separate right now. I need to force this into the file system. But basically, it has the SID, it has the name, it has the UID and GID, which you can look up using LDAP, or whatever name service you want. It just has a list of ways that all these things map to the same identity. And that's just used for access control, or for file ownership. So when you come in over the wire and you say I'm ID 99, and somebody else comes in and has with a SID, that file is owned by the same identity within the file system.
And where is that being maintained?
In the file system. The file system itself has an identity that is like a super-cred. And NFS maintains the list of groups. We have the metadata server, we call it Protod. It's basically an NFS server. It can also look up identities and populate this ident structure. So basically, whichever protocol you come in, you have to be identified by one of these ident structures. If we don't have one, we'll create a new one. If one already exists, then it'll just look up and use it.
Within one enclosure, you're going to have one set of software dealing with any drives.
You're looking blank, but we can talk more if you want. It's not dissimilar to what was done in Waffle in some ways, but there is no user.map and group.map. You don't, if you want mapping, say in a Windows environment, then you have to go to Windows and set up the Unix ID and map that to your Windows identity. We don't provide a user mapping service per se.
That it still is open because the host is still managing large data, the host expense size here.
And I was going to talk a little bit about how this works in Nginx, which will give you an idea of the architecture. So Nginx is kind of similar to Samba, for those of you familiar with that. It has a master process, has a bunch of worker processes. One of the differences is in Nginx is the master process communicates via shared memory to the workers, and the typical recommendation from Nginx is that you run one worker per CPU core that you want it to run on. So if you want to allocate 16 cores, then you want to run 16 processes. The master process reads all the configuration, so refresh is easy. You just signal the master process, it rereads the configuration, posts it in shared memory, and then all the workers can see that shared configuration. And one of the benefits of REST over SMB is there's no stateful session. So every request can come in and look at the configuration. You don't need to tear down sessions and reestablish sessions. Every request is unique and carries all its state. So once you refresh the master process, the next request will pick up the new configuration. Any requests that are in process will complete with the existing configuration. All of the I/O is handled by the worker process. And the nice thing for me is it handles all the HTTP and HTTPS stuff, the certificates, the headers, the query params. I receive that as post-processed data, and I'll go into where the module, the S3 module, sits relative to Nginx in a second. The workers use a phase and pipeline model. So you can plug your module into any phase and anywhere in the pipeline. So you can be pre-configuration, post-configuration, post-parsing, wherever you want to fit in the pipeline. You just insert your module at that place within Nginx. The one disadvantage of Nginx is it has zero documentation. So you get to read lots and lots of C code to figure all this stuff out. Any questions on this? So this is the pipeline model. So you have the client, sends HTTP. It goes through the Nginx pipeline. When it hits the module that when it hits my S3 module, I take over the request. I get to process all the parameters and the blocks and any data that's been sent. And it's my module's responsibility to respond to the client. So nothing downstream from me sees that request. There is a plug-in mechanism where you can actually pass on. So if you want to process some data, but you still want the rest of the pipeline to flow, you can pass it down. S3 is just an endpoint. So once it hits my process or my module, I process it to completion and send the response.
Generally, you can expect that each RUA requires...
And just going back to the Hammerspace architecture, so the idea of Hammerspace, again, is to take all of these data silos, all these separate NAS boxes, provide a global namespace, regardless of whether the NAS is at your site or some other site. It doesn't matter. Everything, all the metadata from all the sites is consolidated. If you make changes at another site, the sites will replicate the metadata first, and then it can pull the data either in the background or on demand. If you ask for the data immediately, it will pull it across. If you don't, then it goes in a pipeline or thread pool, and it pulls it across in the background. And as I said, the S3 process, S3 module is used both for that replication process and also to push and pull data from the cloud and also to feed into these AI pipelines. I think that's about it. If anyone has any questions.
So that also can mean that there's
what is it that you track? Do you have like an existing S3 data somewhere presented through like a single namespace, or you provide
any
access to
so the question is, do I have a special S3 data store, or is it just part of the single namespace? The answer is it's just part of the single namespace. So if you store files using NFS or S3, NFS or SMB, you can view them as objects over S3. If you have an object store, then we can aggregate that object store and present that data as part of our namespace. So remember that we're just a metadata service, so all we maintain are the attributes, the timestamps, the file size, the directories, the file names, the object names. We don't control the data on the back end. The data always stays where it was originally located, but we can present that as part of our namespace. Go ahead.
So if you've got this namespace, you're presenting that over NFS?
Yeah, so the question is how does the data get presented if I have an S3 backend?
Well, the question was if they then write that using NFS write, and it's on a immutable object store.
So what happens if the backend store is immutable and you present the S3 namespace and then somebody tries to do an NFS write? It's just like trying to write to a snapshot or trying to write to a read-only volume. It will fail. Yeah. I mean, if the backend is immutable, then you can't modify it. So, and that should be flagged when you mount it. So we actually mount the namespace of the other system, and we actually create some infrastructure on that system using hard links and whatnot. So if it's mounted read-only, then it's a read-only namespace. One thing is the backend store would have to, so you can import S3 into our system, but to do what we call a simulation, I leave the data on the original system, that original system has to support NFS v3. That's how our assimilation engine. We can do NFS assimilation, we can do SMB assimilation, but you need those protocols to be supported. So if it's a pure object store, you would actually have to replicate the data to some NAS or into. So our system can also provide storage. You can use the portal nodes, the ones that are running the NFS and the SMB servers. So you've got the metadata nodes, we call that the anvil, and we have portals that run the protocols. The portals themselves can have storage, or you can use some other NAS box as the backing store. So for a pure S3 backend, you would have to replicate that into our system in order to present it over NFS and SMB. Go ahead.
I'm not sure I understand. Is this open source? What part is? What part isn't?
So everything is. Yeah, so is it open source? What parts are open source? What parts are not? All of the NFS stuff, all of the Linux stuff, as I said with the Meta example, they're using their own Linux servers as portals. That's not our code, that's just their systems. So anything that's standard NFS, anything that's standard Linux will just work. We drive the features through the standards body, the NFS standards body, to try and make the features standard across the Linux and Unix world. The S3, so Nginx is open source. The S3 module isn't open source. In fact, David Flynn, our CEO, actually asked me if we should open source it. There's nothing special about it. It's just a bunch of C code that parses S3 protocol. There's nothing secret. If there's interest amongst this community about taking that code, I can talk to David. I don't think there's any barrier to that. It's not open source today, but there's nothing prohibiting it being open source. The only part of this that's truly, there's two parts that are truly proprietary. One is the key value store, the metadata server. So not the pNFS implementation, but the underpinnings of the file system, that's proprietary. And then the replication engine is also, they call it the data mover. It's calling into the S3 service to do the data movement, but it has a very complex algorithmic component to do alignment. So you have these objectives where you tell the system which tiers you want the data on, which resilience you want for particular data, and the resilience is measured against the back end. So if you have a highly resilient back end, you may only have one copy. If you have a back end with low resilience, like it's a single NAS node, we may make multiple copies across different back ends. That data mover code is all proprietary. That's custom. And I doubt that's going to be open sourced. But to a large extent, I mean, other than those two components, most of it's just standard Linux and standard protocols and Samba.
Was there any study if there is any impact on the performance of NAS 1, NAS 2, instead of directly going to that additional layer?
So there is a desire where
if it is impacting performance, how much?
So the question is what's the impact and performance of having these backends and the introduction of our layer? The only place where we come into the path is when you ask metadata questions. So if you're doing a reader, then that data comes from Hammerspace. If you're doing I/O, the client is talking either through our portal to the backend NAS box, or going direct. If it's an NFS 4.2 mount, it will go direct. It'll get a layout and it'll go direct to the backend box. So if you go through our portal, there may be a small overhead as we act as a proxy. If you don't like that overhead, then you can just mount NFS 4.2 and go direct to the NAS. So the real ability to deliver data is coming from the backend NAS.
Otherwise, I would not give it
when you're interacting with a file, read-only, sure, it's going to be the file load, but if you're writing to the file and you can change the size, you change the sound, how does that get back to the metadata server?
So the metadata server gives a layout to the client. When the client makes a change, it has to report that back via the layout recall. So when it closes to the metadata server, then we may actually talk to the storage to find out what changed. So we don't know how much you wrote or what you did on the back end until we interrogate the back end. If it's on our system, then it's easy because it's in fact, there is a, so you asked about performance. If our portal nodes are acting as the storage, we have a bypass in the kernel. And this is being pushed through the standards body right now, the NFS standard. It doesn't go over NFS if the data is local to the portal. So if you're using the portal as a storage server, if you backed it with NVMe or something, then your reads and writes are just going direct through the VFS to the storage. It's not going through NFS at all. So that works really well if you have storage locally. If you're using the back end, then you do go over NFS v3 to read and write the data in the back end. But we do have what we call reflected get attrs going to the back end storage. So the metadata server has to make sure that whatever you did on the back end server is reflected in our metadata. And it may have to send get attr requests to the back end.
Is it proactive?
It's usually on demand. So so there are a lot of background activities where it will do, it's almost like a self-healing thing where it will have to, the file will be marked out of alignment, the same as if you have a file that's been modified remotely, but you've never seen the content. That file is out of alignment, and the file system will send objective requests to the data mover to bring things into alignment, or it will go talk to the backend service to bring the attributes back into alignment. But we have this notion of whether things are in alignment or out of alignment. If you ask a question, if you come with a get attr from a client and it's not aligned, we have to go get that data. We have to go get that metadata.
The question is, actually, let me go to the question image so that we can point to it. The question here is, the host extends is
Silence.
Does this handle striped files?
It will do all sorts of striping and mirroring, and David alluded to things like NConnect, where it can make multiple connections to use increased bandwidth. But yes, we have a back end that does erasure coding as well. So it does all sorts of, in fact, NFS 4.2 has an extension to do mirroring as well. So you can create multiple copies, or you can create mirrors. And it's actually the NFS 4.2 client that takes care of that. So it doesn't force the work onto the metadata server. You're telling the client, I want to have 3 mirrors of this data. It will make 3 copies on 3 different storage systems. And that's all being pushed through the NFS standard. I don't know if it's been standardized yet, but I know it's proposed. I don't know if do you know if it's been?
I think it's proposed.
Okay.
Last time I looked at the RC.
Yeah, so anything we do like that through NFS, we try to make it part of the standard because we need the clients and the servers to work in harmony.
So the question is, for smaller hosting stacks, there will
If
be
not,
less GC.
no more questions.
And that's true, that is showing
Thank you very much.
here.